Last thing I wanted to address in this adversarial search lecture is to talk a little bit about stochastic games or non-deterministic games. So these are games in which we have some random element occurring during the game. It could be throwing a die or dice, or actually shuffling cards. So this can include the chance node in the search. We don't have anymore only max and min. We also have nodes for chance to occur between the two players. So an example of a game is the backgammon, that actually is one of the one of the oldest board games combining skills and chance of the players. The goal is that, given the board like this one, the goal is that each player needs to get rid of his pieces as soon as possible before the other one does. So I'm not going to go into the details of how the game works, but I wanted to show you that in this case, the game tree is actually slightly different from the previous, what we have seen so far for tic-tac-toe and for our toy examples, and also for chess, where there is no chance factor occurring. So in this case, we're going to have an alternation between max, chance, min, chance, max, etc. So we're going to have our regular max and min working and playing, but also we have this element of chance occurring in the middle between them. So we're going to actually have, in the case of backgammon, we are actually rolling two dice, which means that we're going to have each numbers on the die occurring with some probability. So we could have 1 occurring with a probability of 1/36. So we have 6 faces on each of the die. So for the backgammon, the search space is no longer max and min playing just by themselves. There will be an element of chance in the middle that actually is symbolized here by the yellow circles. And each of the yellow circles has some branching factor that actually shows the possible outcomes of rolling a die or rolling dice or shuffling a card. So for example, for the backgammon game, we are going to have an outcome on the 2 dice that actually could be either 1-1 with a probability of 1/36, or 1-2 or 2-1 with the probability of 1 divided by 18, and so on and so forth. So I'm going to put all the possible outcomes weighted by the probability of the event for happening. So we need to take into consideration this new element in the search game in order to find the best solutions for max. So the algorithm that could handle this randomness in the game is called expect-minimax, that actually generalizes the minimax algorithm to handle the chance nodes as follows. So this is a very similar function that we have seen for minimax, in which we are going to have, if the state is a max, we are going to call expect-minimax on all the successors or all the children of the state. If the state is a min, we are going to call again all the expect-minimax for all the successors of the state to minimize for min. But if the state is a chance state, then we are going to call expect-minimax and return the average of the value of the successors. So we know that there will be a chance to get with different probability, we have different outcomes. So we're going to weight that by the probability of each outcome to happen and get the expected value of those outcomes. So let's take a very simple example with coin flipping. So suppose we have an unbiased coin. So we flip it, we get a head with a probability of 0.5, we get a tail with probability of 0.5. So suppose we have max playing here and min playing here, and we have this terminal states here with these values. So the way that expect-minimax would work is to, first of all, get so this is the min value. So we're going to get, at this point, the value of 4. For this one, we're going to get 6. For this min value, we're going to get 2. And for this one, we're going to get 1. So remember that we are going to have max pick the maximum value of its children. But it is actually, we have the chance in the middle here that actually gives the chance of getting this outcome here with a 50% and the chance of getting this outcome here with 50%. So I'm going to use a weighted sum of these two outcomes here and do the average of 4 and 6, which will lead us to actually 5. So we get 5 here. And here it's going to be 2 plus 1 is 3 divided by 2. So this is the average of the outcome weighted by the probability here of 0.5 for each of the outcomes of the flipping the coin. And we will have a value of 1.5. And then the max will take the maximum value of these two outcomes and we'll end up with 5. So this is how we are going to weight actually the min value that is being sent back by min from the leaves by these chance nodes. And we're going to, of course, use, so this is a simple example with coin flipping. You could imagine with rolling a die, we have different probabilities depending on the different outcomes we get. This is just to give you a flavor of what stochastic games would look like and how we would change the minimax algorithm to handle that randomness in the search. The function expecting minimax in this case will look like the minimax function, with the exception that we are going to introduce a third condition here in which we consider the case for chance. If it's a chance node, then we're going to calculate the weighted sum of the probability of the outcomes for this node, just as we did now. So we take the weighted average, or the expected value of the outcomes of the nodes starting from this position. We are reaching now the end of the adversarial search lecture, in which we have seen that games are modeled in AI as search problems and use a heuristic to be able to evaluate the game. So it's a complicated problem for AI, but it has proven to be actually a problem that's solvable for many complex games such as chess or Go. So we have good algorithms for those. We have seen that the minimax algorithm chooses the best it should be here the best move given the optimal play from the opponent. Minimax goes all the way down into the leaves, which is impractical given time constraints, and often we use strategies such as alpha-beta pruning that allows to reduce the search space and the game tree by pruning parts of it. This will allow us to go deeper and in the tree with the same time constraints, which actually turned out to make a big difference when we search a tree for the best possible strategy to solve the problem. We could also use, besides pruning, some bookkeeping, some evaluation heuristics, node reordering, and also IDS, or iterative depth search techniques, has proven to be not only effective but also efficient within the time constraints in practice. And that's why we have seen lots of progress in the last years in solving games that are very complex, as I said, such as chess, Go, etc. I wanted to finish by saying that games is an exciting and fun topic for artificial intelligence, because devising adversarial search agent is challenging because of the huge state space. So it pushes the boundary of the research in AI, and this could be applicable in other domains besides games. In this lecture, we have just scratched the surface of this topic. Further topic could be explored, and this includes partially observable games in which we have partial information. For example, if you play poker or bridge, you don't know what are the cards in your opponent's hand, so you don't have a full visibility of the game as compared to chess, in which you could see the whole board. Another point to mention about games and AI is that, except for robot football, known as soccer in the US, there was no much interest in AI in modeling physical games, such as tennis or other ones. So I invite you to check this website, robocop.org, in which you are going to see really cute soccer games played by robots. Finally, if you are interested in chess, check out the evaluation functions in COLAIAIX paper. That's a very interesting read. And the last point is that you will have a chance to implement a game in your homework assignment, so have fun, and I will see you in the next lecture.